This is the EdExcel Advanced Extension Award Maths paper from the 2019 series. Question number 1. By writing u equals log base 4 of r, where r is greater than 0, we have to show that log base 4 of r is equal to 1/2 times log base 2 of r. So for part A, we begin with u equaling log base 4 of r. And if we anti-log both sides, we have 4 to the power of u equals r. Now we will take log base 2 of both sides because the question involves log base 2. So taking log base 2 of both sides, we have log base 2 of 4 to the u equals log base 2 of r. And so using the power law, we would end up with u times log base 2 of 4 equals log base 2 of r. And recognizing that log base 2 of 4 is 2, because 2 to the power of 2 equals 4, on the left hand side we have 2u, and on the right hand side we have log base 2 of r. And if we divide both sides by 2, that would mean u is equal to 1/2 times log base 2 of r. And using the fact that u is equal to log base 4 of r, we can therefore conclude that log base 4 of r is equal to 1/2 times log base 2 of r. For part B of the question, we have to solve the equation log base 4 of 5x squared minus 11 equals log base 2 of 3x minus 5. So with this equation, you will first of all notice that the bases are different. Now we begin this question by anti-logging both sides. And if we anti-log both sides, on the left hand side we have 4 to the power of log base 4 of 5x squared minus 11, and on the right hand side we have 4 to the power of log base 2 of 3x minus 5. Now on the left hand side, 4 to the power of log base 4 of 5x squared minus 11 is just 5x squared minus 11. But on the right hand side, we've got 4 to the power of log base 2 of 3x minus 5. And what we can do is recognize that 4 is the same as 2 squared. So we have 2 squared, and then 2 squared is being raised to the power of log base 2 of 3x minus 5. So we have 5x squared minus 11 equals 2 to the power of 2 times by log base 2 of 3x minus 5, and therefore if we use the power law, 2 to the power of 2 log base 2 of 3x minus 5 is the same as 2 to the log base 2 of 3x minus 5 squared. And therefore, we have 5x squared minus 11 equaling 3x minus 5 squared. And so, 5x squared minus 11 is equal to 9x squared minus 30x plus 25. And if we simplify, we have 4x squared minus 30x plus 36 equals 0. And now if I divide both sides by 2, we end up with 2x squared minus 15x plus 18 equals 0. And factorising, we have 2x minus 3 multiplied by x minus 6, and this is equal to 0. And so therefore, we've got solutions x equals 3 over 2 and x equals 6. Now, if we go back to the original problem, when x is equal to 6, here I've got 36 times 5 minus 11, that's positive. Here I've got 3 times 6 minus 5, that's positive, so x equals 6 works. But when x equals 3 over 2, well, 5 times 3 over 2 squared minus 11, that's positive, but then 3 times 3 over 2 minus 5, that's negative. And so, what we can see then is 3x minus 5 is less than 0 when x is equal to 3 over 2. And so what this means then is log base 2 of 3x minus 5 is undefined at x equals 3 over 2. And so therefore, x equals 6 is our only solution. Question 2. The discrete random variable x follows the binomial distribution. X follows binomial distribution with parameters n, p, where p is in between 0 and 1, and the mode of x is m. For part A, we have to write down in terms of m, n, and p an expression for the probability that x is equal to m. Well, for part A of the question, the probability that x is equal to m, we have n, choose m, multiplied by p to the m, multiplied by 1 minus p to the n minus m. For part B of the question, we have to determine, in terms of n and p, an interval of width 1 in which m lies. Well, here we've got some sort of a distribution, and we know that m is the mode, which means the probability that x is equal to m would correspond to the peak. Now, either side, we've also got other probabilities. For example, on this side, because we've got an interval of width 1, here we've got the probability that x is equal to m minus 1 for this peak. And similarly on the other side, we've got the probability that x is equal to m plus 1. Now in this question, because we are considering probabilities of a binomial distribution, we will be making use of the n choose r formula throughout. And n choose r is equal to n factorial over r factorial times n minus r factorial. Now what exactly do we want in this question? Well, what we want is the probability that x is equal to m minus 1 to be less than the probability that x is equal to m. That makes sense because m would correspond to the mod and we've got a width of 1. Or we've got the probability that x is equal to m plus 1 being less than or equal to the probability that x is equal to m. Now, the reason this probability and this probability is less than or equal to the probability that x is equal to m is because the probability that x is equal to m is the mod, it's the most common, which means its probability is the highest. So now we can work out each of these bits. The probability that x is equal to m minus 1, that's n choose m minus 1, multiplied by p to the m minus 1 times 1 minus p to the n minus, and then in brackets m minus 1. And if we simplify this, we have n factorial divided by m minus 1 factorial times n minus, and then in brackets m minus 1 factorial, multiplied by p to the m minus 1, multiplied by 1 minus p to the n minus m plus 1. Notice the negative and the negative give this positive. Now, if we tidy this up even further, we have n factorial divided by m minus 1 factorial multiplied by n minus m plus 1, again the minus and the minus give this plus, multiplied by p to the m minus 1 times 1 minus p to the n minus m plus 1. Now the probability that x is equal to m, well, we calculated that in part A, and so if we simplify, we have n factorial divided by m factorial times n minus m factorial times p to the m times 1 minus p to the n minus m. And now if we calculate the probability that x is equal to m plus 1, well, we have n choose m plus 1 times p to the m plus 1 times 1 minus p to the n minus, and then in brackets m plus 1. So now we can tidy all this up. We have n factorial divided by m plus 1 factorial multiplied by n minus, then in brackets m plus 1, then factorial, times p to the m plus 1 times 1 minus p to the power of n minus, then in brackets m plus 1. And if we tidy this up, we get this result shown here. N factorial divided by m plus 1 factorial times n minus m minus 1 factorial times p to the m plus 1 times 1 minus p to the n minus m minus 1. Now, let's first of all consider this condition here. So for this condition, we've got the probability that x is equal to m minus 1 being less than or equal to the probability that x is equal to m. And those expressions are shown here. Now, what we need to do is simplify all this. First of all, you will find the n factorials cancel on both sides. So what we are left with is p to the m times 1 minus p to the n minus m plus 1 divided by m minus 1 factorial times n minus m plus 1 factorial, and this is less than or equal to p to the m multiplied by 1 minus p to the n minus m, and then we are dividing this by m factorial times n minus m factorial. So now let's see how we can simplify this. Well, let's think about what we have for our denominators. Here we've got m minus 1 factorial times n minus m plus 1 factorial. Now, I can see that the n minus m plus 1 factorial is the same as n minus m plus 1 multiplied by n minus m factorial. So, this bit is the same as what we have here. And then the top bit remains the same, p to the m minus 1 multiplied by 1 minus p to the n minus m plus 1. Now, on the right hand side, m factorial can be rewritten as m multiplied by m minus 1 factorial, and then we have this n minus m factorial. And on the top, we've got the p to the m times 1 minus p to the n minus m. Now well, let's just clarify what we said here. M factorial is the same as m times m minus 1 factorial. And what you will notice is the m minus 1 factorial cancels with this m minus 1 factorial, and the n minus m factorial cancels with this n minus m factorial. So what we have then is p to the m minus 1 times 1 minus p to the n minus m plus 1 divided by, then here we've got n minus m plus 1, and this is less than or equal to, well, here we have p to the m times 1 minus p to the n minus m, and then we divide this by m. Now let's try to simplify this even further. Well, p to the m minus 1 is the same as p to the m divided by p, and I'm multiplying this by 1 minus p to the n minus m multiplied by 1 minus p to the 1. And then this is being divided by n minus m plus 1. And this is less than or equal to p to the m multiplied by 1 minus p to the n minus m divided by m. And then hopefully you see the p to the m cancels. Then we have 1 minus p to the n minus m cancelling. And therefore, on the left hand side, we have 1 minus p divided by p divided by n minus m plus 1. This is less than or equal to 1 over m. And so, if we multiply through by p, what we have then is 1 minus p over n minus m plus 1 being less than or equal to p over m. Now we'll call this 1 for a moment. Now let's consider this condition. So if we now consider condition 2, if we use our expressions, so we've got the expression for the probability that x is equal to m minus 1 being less than or equal to the expression for the probability that x is equal to m. Now, as before, the n factorials cancel, so that means we are left with p to the m plus 1 times 1 minus p to the n minus m minus 1, and then we are dividing this by m plus 1 factorial times n minus m minus 1 factorial, and this is less than or equal to p to the m times 1 minus p to the n minus m, and then I'm going to divide this by m factorial times n minus m factorial. Now, as before, we can rewrite some of the factorials. So, if we were to rewrite some of the factorials, then what we can do is, well, here the m plus 1 factorial is the same as m plus 1 times m factorial. So that comes from here. Then I've got n minus m minus 1 factorial, can't do much with that just yet. And on the top, I've got p to the m plus 1 times 1 minus p to the n minus m minus 1. And this is less than or equal to, now m factorial, we're going to leave that alone. And the n minus m factorial, I can rewrite that as n minus m times n minus m times minus 1 factorial. So this bit is the same as this bit over here. And on the top, we've got p to the m times 1 minus p to the n minus m. So now let's see what cancels. Well, the m factorial cancels, and so does the n minus m minus 1 factorials. Those cancel. So I'm left with p to the m plus 1 times 1 minus p to the n minus m minus 1. And I'm going to divide this by m plus 1, and this is less than or equal to, now here I've got p to the m times 1 minus p to the n minus m divided by, now here I've got n minus m. So now let's see how we can simplify all this. Well, p to the m I can write as p to the m times by p, then I've got 1 minus p to the n minus m, and then I've also got this being divided by 1 minus p, and then the entire thing is being divided by m plus 1, and this is less than or equal to p to the m times 1 minus p to the n minus m, and then I'm going to divide this by n minus m. So now if we think about what cancels, the 1 minus p to the n minus m cancels, the p to the m cancels, so I'm left with, over here, p over 1 minus p over m plus 1, and this is less than or equal to 1 over n minus m. So if I multiply through by 1 minus p, that means I'm left with p over m plus 1 being less than or equal to 1 minus p over n minus m. Now I'm going to call this 2. And what we need to do now is find, if we go back to the question, we need to find an interval, which means we need a range of values for m. So from 1, we've got 1 minus p over n minus m plus 1 being less than or equal to p over m. So if I multiply through by m, we have m multiplied by 1 minus p being less than or equal to p multiplied by n minus m plus 1. So I've got m minus mp being less than pn minus mp plus 1. Now the mp's cancel on both sides, so I've got m being less than or equal to pn plus p, and from this we can see then m is less than or equal to p multiplied by n plus 1. Now I'll call this 3 for now. Now from equation 2, we've got p over m plus 1 being less than or equal to 1 minus p over n minus m. And if I cross multiply, we have p multiplied by n minus m being less than or equal to m plus 1 times 1 minus p. So I've got pn minus pm being less than or equal to m plus 1 minus pm minus p. So I've got pn minus pm, well, we can see what simplifies, that's the minus pm's, those simplify to 0. So I've got pn being less than or equal to m plus 1 minus p, and if I add p to both sides, pn plus 1, well, I have pn plus p rather being less than m plus 1, subtract 1 from both sides, so I've got pn plus p minus 1 being less than or equal to m, and if I factorise the p out, I've got p times n plus 1 minus 1 being less than or equal to m. I'm going to call this 4. So now we've got condition 3 and condition 4. So combining 3 and 4 into a single inequality, we can therefore conclude that p times n plus 1 minus 1 is less than or equal to m, which is less than p times n plus 1. And so, here is our solution. For part C of the question, we have to find a value of n where n is greater than 100 and a value of p where p is less than 0.2, for which x has two modes. For each chosen values of n and p, we have to state these two modes. So, we can choose any value of n and p such that n is greater than 100 and p is less than 0.2, and we require the endpoints of the intervals of length 1 to be integers, and that's because m must be an integer. So, if we take a look at our inequality, let's try a probability such as p equals 0.1. So what would my interval be? Well, I would have 0.1 times n plus 1 minus 1 being less than or equal to m being less than or equal to 0.1 times n plus 1. And you will recall that we want the endpoints of these intervals to be integers, which means the 0.1 times n plus 1 minus 1 and the 0.1 times n plus 1, these are integers. Now if I think about it, I've got 1/10 of a number which I want to be an integer, and I want n to be greater than 100. Well, can I have n equaling 101? Well, I can't, because 0.1 times 102 won't give an integer. But what we could have with p equaling 0.1 is, well, we could have, in this case, n equaling 109, which means I've got 0.1 times 109 plus 1 minus 1 being less than or equal to m being less than or equal to 0.1 times 109 plus 1. So I've got 110 times 0.1 minus 1, so that's 10. This is less than or equal to m, and this is less than or equal to, now let's just double check this. We've got 110 minus 1, so here we've got 9, and here we're going to have 10. So we could have two modes then. What we can say then is the modes could be 9 and 10. Question number 3. We are given that phi is equal to 1/2 times root 5 plus 1. And for part A we have to show that for the first part, phi squared is equal to phi plus 1. So for part A, given what phi is, phi squared on the left hand side will equal 1/2 times square root 5 plus 1 squared. And so 1/2 all squared is a quarter. So we've got 1/4 multiplied by root 5 plus 1 all squared, which I'm going to write as root 5 plus 1 times root 5 plus 1. And if we work this out, we've got 1/4 multiplied by, now root 5 times root 5 is just 5, and we've got root 5 times by 1 twice, so that's 2 root 5, and then we've got 1 times 1, which is 1. So what we end up with over here then is 1/4 multiplied by 6 plus 2 root 5. And if I factorize out a 2, we have 1/2 times by root 5 plus 3. Now on the right hand side, we have thigh plus 1. So we have thigh, which is 1/2 times by root 5 plus 1, and then we are adding another 1. So we've got 1/2 times by root 5 plus 1 plus, and then here we have 2 over 2. So if I factorize out a 1/2, we end up with 1/2 times by root 5 plus 1 plus another 2, leaving us with 1/2 times by root 5 plus 3. And that's what we had on the left hand side. So what we can say then is, as the left hand side is equal to the right hand side, we can therefore conclude that thigh squared is equal to thigh plus 1. Now for the next part, we have to show that 1 over thigh is equal to thigh minus 1. So on the left hand side, we have 1 over thigh. So that what this is equal to is 1 over one half times by root 5 plus 1, which is the same as 2 over root 5 plus 1. And now what we can do is multiply the top and bottom by the conjugate of the bottom. We rationalize, so we multiply the top and bottom by root 5 minus 1. It's as though we are multiplying by 1. So, expanding, along the top we've got 2 root 5 minus 2, and on the bottom we've got root 5 times root 5, which is 5, and then 1 minus 1, which is minus 1. So we've got 2 root 5 minus 2 divided by 4. So we've got here 2 over 4, which is a half. So we end up with 1/2 times by root 5 minus 1. And then on the right hand side, we have thigh minus 1, which is equal to 1/2 times by root 5 plus 1 minus 1, So we've got 1/2 times by root 5 plus 1/2 minus 1/2. So we've got 1/2 times by square root 5 plus 1/2, because a half, rather, minus 1. And here we get minus 1, because a half minus 1 is minus a half. And if I factorize out the 1/2, we've got 1/2 times by root 5 minus 1. And therefore, what we can see then is, as the left-hand side is equal to the right-hand side, we can therefore conclude that 1/thigh is equal to thigh minus 1. For part B of the question, the equations of the two curves are y equals 1/x where x is greater than 0, and y equals the natural log of x minus x plus k where x is greater than 0 and k is a positive constant. The curves touch at the common point P, and we have to find, in terms of thigh, the coordinates of P and the value of k. So for part B, the curves touch when their derivatives are equal. In other words, they've got a common tangent. So here we can see our two curves, they've got this common tangent, and that's when the two curves touch each other, when their derivatives are equal and they've got a common tangent. So for part B, if I've got y equals 1/x, then I can differentiate this. Dy over dx will equal negative 1/x squared. And if I've got y equals the natural log of x minus x plus k, I can differentiate this. Dy over dx is equal to 1/x minus 1. K is a constant, so differentiating that we get 0. Now we need to set the derivatives equal to each other. So I've got minus 1/x squared, and this will equal 1/x minus 1. And so if that's the case, then we've got minus 1 equals x minus x squared. X squared minus x minus 1 is equal to 0. Now completing the square, we have x minus 1/2 squared minus the square of this, which is 1/4, and then we are subtracting 1. So this subtract 1 I'm going to rewrite as subtract 4/4. So this is all equal to 0. So we've got x minus 1/2 squared, and here we've got minus 5/4, and if I take that over to the right hand side, I've got x minus 1/2 all squared equals 5/4. So that means x is equal to 1/2 plus minus 1/2 times the square root of 5, and as x is greater than 0, that means for our solution, we have x equals 1/2 plus 1/2 times the square root of 5. And so, if we have x equals, now here I'm going to factorize out the 1/2. If I've got 1/2 on the outside, that means inside the bracket I can have the root 5 plus 1. And because I've got this result, if we recall from what 1/2 times root 5 plus 1 is, that's theta. And so therefore, this value here is equal to phi. So, the x-coordinate of P is phi, which would imply for the y-coordinate, now for the y-coordinate we can substitute back into here, the y-coordinate will be 1/phi. So, knowing what x and y are, we can therefore conclude the coordinates of P, we've got phi and 1/phi. Now, for the next part of the question, we have to find the value of k, and we can do this by using this here. Now, 1/phi, we have shown that to be the same as phi minus 1. So this 1/phi we can rewrite as phi minus 1. And therefore, when x is equal to phi and y is equal to phi minus 1, in other words, what p is, we have phi minus 1 equals the natural log of phi minus phi plus k, in which case we can conclude k is equal to 2 phi minus the natural log of phi minus 1. Question number 4. For part A, we have to prove the identity sin x plus cos y multiplied by cos of x minus y is equivalent to 1 plus sine of x minus y multiplied by cos x plus sine y. Now, what we will do is we will begin on the left hand side and try to get to the right hand side. So for part A, on the left hand side, we have sin x plus cos y multiplied by cos of x minus y. Now what we can do is use the double angle formula. So, using the double angle formula, well, first of all, we have sin x plus cos y, and then using the double angle formula, we would have cos x cos y plus, remember if here we've got a minus, we need a plus here, sin x sin y. And then, if I expand out, we have sin x times by cos x cos y, so that will be sin x cos x cos y. Then we have sin x times by sin x times by sin y, so that will be sin squared x sin y. And then we have cos y times by cos x times by cos y, so that will be cos x cos squared y, and then we've got cos y times by sin x times by sin y, so that will quite simply be sin x times by cos y times by sin y. So, recognizing that sin squared is 1 minus cos squared, well, we still have sin x cos x cos y, and then I'm going to add on to this 1 minus cos squared x times by sin y, and then I'm going to add on to this, well, I can recognize that cos squared y is the same as 1 minus sin squared y. So I've got cos x times by 1 minus sin squared y. And then I'm going to add on to this sin x cos y sin y. So now let's simplify even further by expanding the brackets where necessary. I've got sin x cos y plus, now here I've got 1 times by sin y, that's sin y, and then I've got minus cos squared sin y, so I've got minus sin y cos squared x, and then I've got cos x, and then I've got minus cos x sin squared y, and then I've got sin x cos y sin y. So now that we've expanded, we can now simplify this even further. Now what I'm going to do is I'm going to write this as cos x plus sin y, and then from the term here and also here, I'm going to factorize out a cos x, and then inside the bracket I would have sin x times by cos y and then I've got minus, then if I consider the term over here, I would have cos x sin y. And then from this term and then this term, I'm going to factorize out a sin y. And then inside the bracket, I would have sin x cos y minus, now here I would have cos x times the sine of y. Now what you will recognize, sin x cos y minus cos x sin y is the same as sine of x minus y. So we've got cos x plus sin y plus cos x multiplied by sine of x minus y plus the sine of y multiplied by sine of x minus y. Now, what we can do from this is factorize out a cos x plus sine y. And if I do that, then here cos x plus sine y times by 1 would give cos x plus sine y. And then here I've got the cos x on the outside and the sine y on the outside of these brackets. And so what I need to do now is add sine of x minus y. And so here is what we have on the right hand side. So because this result is equivalent to the right hand side, the result is shown to be true. For part B of the question, hence or otherwise show that sine of 5 theta plus cos of 3 theta over cos of 5 theta plus sine of 3 theta is equivalent to 1 plus tan theta over 1 minus tan theta. So for part B, on the left hand side we've got sine 5 theta plus cos 3 theta over cos 5 theta plus sine 3 theta. Now because the result said hence, what we would have to do somehow is use our result to part A. And the way we will use our result to part A is by letting x equal 5 theta and letting y equal 3 theta. And so what we would have on the left hand side then is sine x plus cos y divided by cos x plus sine y. And what we can do is use our result to part A. Notice here we've got a sine x plus cos y and a cos x plus sine y. And here we have those results in some way. So what we will do is use those ideas. So here is the result in part A, and therefore if we rearrange, we can see then that sine x plus cos y divided by cos x plus sine y, this will be equivalent to 1 plus sine of x minus y divided by cos of x minus y. And so that's what we have here. And therefore, what we have is sine x plus cos y over cos x plus sine y being the same as 1 plus sine of x minus y divided by cos of x minus y. And I know what x is, that's 5 theta, and I know what y is, that's 3 theta. So I've got 1 plus the sine of 5 theta subtract 3 theta divided by cos of 5 theta minus 3 theta. So I've got 1 plus sine 2 theta divided by cos of 2 theta. And so what we need to do is somehow show that this is the same as 1 plus tan theta over 1 minus tan theta. And the way we can do that is to recognize that 1 is the same as cos squared theta plus sine squared theta, and then we add on sine 2 theta, which is the same as 2 sine theta cos theta. And on the bottom, cos of 2 theta we can write as cos squared theta minus sine squared theta. Now, let's rewrite this as cos squared theta plus 2 sine theta cos theta plus sine squared. And then I'm going to divide this by cos squared theta minus sine squared theta. On the top, I can write that as cos theta plus sine theta all squared. And on the bottom, I can write this as a difference of 2 squares, cos theta plus sine theta multiplied by cos theta minus sine theta. And so the cos theta plus sine theta squared simplifies with the cos theta plus sine theta once. So I'm left with cos theta plus sine theta divided by cos theta minus sine theta. And what we can do now is divide the top and bottom by cos. So if I do that, we have cos theta divided by cos theta plus sine theta over cos theta, and then on the bottom we have cos theta divided by cos theta subtract sine theta over cos theta. And so cos theta over cos theta is 1, sine over cos is tan, and then cos over cos is 1, sine over cos is tan, and that's exactly what we wanted to show. For part C of the question, we are given that k is greater than 1, and we have to show that the equation sine of 5 theta plus cos of 3 theta over cos 5 theta plus sine 3 theta equals k has a unique solution in the interval from 0 to pi over 4. So for part C, we've got the given equation, and using our result from part B, we can rewrite this as 1 plus tan theta divided by 1 minus tan theta. This is equal to k. Now let's rearrange for tan theta. If I multiply through by 1 minus tan theta, then I would have 1 plus tan theta equals k multiplied by 1 minus tan theta. So I've got 1 plus tan theta equals k minus k tan theta. And gathering everything over with a tan on one side, everything that's not a tan on the other side, we have tan theta plus k tan theta equals k minus 1. And if I factorize out the tan theta, I've got 1 plus k times tan theta equals k minus 1. And so tan theta is equal to k minus 1 over 1 plus k, which is the same as k plus 1. So now, what we need to do is show that this has a unique solution in between 0 and pi over 4. Now, what I'm going to do is rewrite the k plus 1, rather the k minus 1 over k plus 1. Now, the way I'm going to approach this I'm going to rewrite, well, what I'm doing, I've got this k minus 1 and I'm dividing that by k plus 1. So using algebraic long division, where I've got the k minus 1 here, k divided by k is 1, and 1 times by k minus 1 is k minus 1. And then if I subtract these, rather here I've got a k plus 1. If I subtract these, rather here, I've got the k minus 1 and here I've got the k plus 1. If I subtract these, then I have minus 2 as my remainder. And so, I've got tan theta equals 1 subtract 2 over k plus 1. And what we can do is think about the behavior of this. So, let's think about what happens as k gets very large. As k gets very large, we have tan theta tending towards 1 subtract 0. So in other words, tan theta tends towards 1. And now, if we go back to the information given in the question, we are given that k is greater than 1. So, because k is greater than 1, then here we've got the k plus 1, which will be greater than 2. Which means that 1 minus the 2 over k plus 1, well, let's think about it. Here I've got 1 subtract a fraction. Now here the numerator is smaller than the denominator because k plus 1 is definitely bigger than 2. So I've got 1 subtract some sort of a fraction. This result here is always going to be greater than 0 because I've got 1 minus some fraction. So that result here is always going to be greater than 0. And so what we can say then, we've got certain conditions. We've got this condition that tan theta is less than 1 because it approaches 1. And we've also got the condition that 1 minus 2 over k plus 1 is greater than 0. In other words, tan theta is greater than this value here. Which means if I combine those inequalities, I've got 0, which is less than tan theta, which is less than 1. And if I take the arctangent of those, I've got the inverse tan of 0, which is less than theta, which is less than the inverse tangent of 1, which means I've got 0, which is less than theta, which is less than pi over 4. Question number 5. Points A and B have position vectors A and B respectively relative to an origin O, and are such that OAB is a triangle with OA equaling A and OB equaling B. The point C with position vector C lies on the line through O that bisects the angle AOB, and what we have to do is prove that the vector BA subtract AB is perpendicular to C. So if we create a diagram to represent this information, so here we've got a diagram. I've got the triangle OAB, I've got the vector A, the vector B, and I've got OA having a length of A and OB having a length of B. Now I've purposely extended the line OA to the point P, and I've extended the line OB to the point Q. The reason for this, if we go back to the question, we want to prove that the vector BA minus AB is perpendicular to C. Now here I've got the vector C, and I've got some point C over here somewhere. So what we are essentially saying here then is the vector OP, so this is the vector OP, that's equal to B multiplied by A. And the vector OQ, that's equal to A times by B. And so therefore, if we find out what the vector BA minus AB is, that's equal to PQ. And what we want to do is show that PQ is perpendicular to C. So let's write down what we've done. So what we've done is we've let P and Q be the points such that OP is equal to BA and OQ is equal to AB respectively. Now, what we can do then is, well, if we go to the question, well, I know that the point C with position vector C lies on the line through O and bisects the angle AOB. And if it bisects the angle AOB, that means this angle is theta and this angle is theta. So what we will do to begin with is find out the magnitude of OP. So the magnitude of OP, that's equal to B multiplied by the magnitude of A, which is just BA. and the magnitude of OQ, that's equal to A times by the magnitude of B, which is AB. And so what we see here then, because BA is the same as AB, that means that the magnitude of OP is equal to the magnitude of OQ. And because of that, because we've got two sides which are equal, that means the triangle OPQ is isosceles. And so, because we've got an isosceles triangle, that means this perpendicular bisector, well, that means the angle bisector from O is perpendicular to PQ. So we've got the angle bisector from O is perpendicular to PQ. Now, if we think about what we want to show, we've got BA subtract AB. So BA subtract AB, so that will be the same as QP. So if I work out what QP is, that's equal to OP subtract OQ. So we have BA subtract AB. So as C is on the perpendicular bisector, we can therefore conclude BA subtract AB, which is the same as QP, that's perpendicular to C. For part B of the question, the point D with position vector D lies on the line AB between A and B. We have to explain why D can be expressed in the form D equals 1 minus lambda multiplied by A plus lambda B for some scalar lambda, with lambda being in between 0 and 1. Well, what we are saying here is we've got the point D which lies somewhere on AB. So let's suppose that D is over here. And therefore here is the vector OD, which we are saying is equal to D. So, to go from O to D, we could go O to A and then A to D. So, to go from O to D, we could go O to A and then A to D. But the problem is we don't know what AD is. But what we do know is since D is in between A and B, that means AD is a fraction of AB. So AD is a fraction of AB, which means that OD is equal to OA plus some fraction lambda of AB. So we have D equals A plus lambda multiplied by, now AB, if we go to our diagram, that's equal to minus A plus B, or B minus A. And now we can therefore conclude D is equal to, now if I think about how many A's I have, I've got 1 minus lambda of them, and then I have 1B. And we also have lambda being in between 0 and 1, as D is in between A and B. That's what we mentioned here. AD is a fraction of A, B, which would imply that lambda is in between 0 and 1. Now, for part C, we are given that D also is on the line OC. And with this, we have to find an expression for lambda in terms of A and B only, and then show that dA to dB is equal to OA to OB. So here's our diagram so far. We've got OC, we've got PQ, we'll leave those alone for a second, but what's important is we've got this point D, which is on AB, and OD lies on OC. Now, what we're going to do is create a new point R, which is also on this line. And the way we're going to do it is to let R be the point such that OP plus OQ equals OR. I will explain what this means. What we're saying here is I'm going to add this point, rather this vector, to the point P, like so, to create this point R, like so. And the result of doing so, if I've drawn my diagram properly, is we'd have this situation here. So we've got this point D, we've got this point C somewhere, I don't know where C is for now, and then I've got this point R. Now, the vector OQ is parallel to PR. So these are parallel. Now, as we know that OP, the magnitude of it, is equal to the magnitude of OR, well, we've added on OQ to the point P to create this line here, PR. So OQ and PR are parallel, and they'd also be equal. Hence, as OP is equal to OQ, so as this length is equal to this length, that would mean that the vectors PR would also, the magnitude of PR would also equal the magnitude of QR. And because of that, we can therefore conclude that OPRQ is a rhombus because each of the sides are equal and parallel. So the diagonals PQ and OR are perpendicular, which means if we consider this statement, here we've got 90 degrees. Now, we can also see that OR is in the direction of OC. So let's write this down. So as OR is in the direction of OC, that means C is equal to some multiple of OR And we know what OR is, that's OP plus OQ. So we have C equaling M times OR. So C is equal to M multiplied by OP plus OQ. And we know what OP and OQ are. If we remember to what we said earlier and go back to our previous diagram, OP is BA and OQ is AB. So what we have here then is the vector C equaling some multiple, because it's in that direction, of the vector BA plus AB. Now, what we also know is D lies on the line containing C. So what we can also say is OC is in the direction of OD. So what we can say then is, as ODC is a straight line, we can therefore conclude that OD is equal to some multiple of OC. I know what OC is, that's just C. So, knowing that, we can therefore conclude that OD is equal to K multiplied by OC, which is M multiplied by BA plus AB. Now, because K and M are just numbers, we can say here then that OD is equal to some multiple N, we'll call it, times BA plus AB. And we know what OD is, that's just D. So we've got D equals N multiplied by BA plus AB. Now, if we remember from part B, we said in part B that D is equal to 1 minus lambda A plus B. So, from part B, we've got D, which is equal to 1 minus lambda A plus B. And because these are equal, we can therefore say that 1 minus lambda A plus B is equal to N multiplied by BA plus AB. So now what we will do is we will equate components. So if I take a look at the A components, on the left I've got 1 minus lambda, and on the right I've got NB. And if I take a look at the B components, I've got 1 on the left hand side, and on the right hand side, rather here, I've got lambda B. So let's just correct this from B. So I've got lambda equals NA. And from this, I can see that N is equal to lambda over A. And knowing what n is, I can replace the n here with lambda over a. So I've got 1 minus lambda equals lambda b over a. And if I multiply through by a minus lambda a is equal to lambda b. And we can find out what lambda is. Well, what we can do is add lambda a to both sides. So I've got a equals lambda a plus lambda b. A equals lambda multiplied by a plus b, which means if I divide through by a plus b, lambda is equal to a over a plus b. Now, what I need to do, if I go back to the question, I need to find out what dA is, what dB is, and what OA is, and what OB is. Well, let's first of all find out what OA and OB are. They're just lengths. So, if I think about what OA is, that's equal to the magnitude of OA, which is just equal to A. And if I think about what OB is, that's equal to the magnitude of OB, which is just B. And therefore, OA over OB is equal to A over B. Now, going back to the question, I need to find out what dA is, starting at D, finishing at A. Well, dA then, that will equal dO plus OA. Or if, well, let's just write that down. If I work out what dA is, I've got minus, well, I've got D to A, I can go D to O, and then O to A. So D to O, that's equal to negative D, and then O to A, that's just equal to A. So I've got negative D, so that's negative. Well, if I remember what D is, that's equal to 1 minus lambda A plus B. So I've got negative 1 minus lambda A plus B. And then I'm adding on to this A. So that's what D was. So if I work this out, I've got here minus, well, I've got the minus on the outside. Then here I've got A minus lambda A plus B plus another A. So what I'd end up with over here then is rather just here realize we need to add on the lambda. So here I've got lambda here. So if I simplify all this, I've got minus A plus lambda A minus lambda B plus A. So I've got lambda multiplied by A minus B. So that's what dA is, and so therefore the magnitude of dA, so let's just write this down, the magnitude of dA, I've got lambda multiplied by a minus b, like so. So that's what dA is equal to. dA is equal to the magnitude of this, which is shown here. Now I need to find out what dB is. Starting at D, finishing at B. So if I work that out, dB, I can go D to O and then O to B. So I've got here DO plus OB. So I've got DO, which is negative D, plus B. So I've got negative, and it's the same thing here. I'm going to have all this repeated. So I've got the result shown here, but this time I'm adding B. So I've got minus A plus lambda A minus lambda B plus B. So if I take a look at the A components, I've got lambda minus 1 A, and if I take a look at the B components, I've got 1 minus lambda B. So we can simplify this to the vector A minus B multiplied by 1 minus lambda. Rather here we've got lambda minus B, rather A minus B times lambda minus 1. So what we can conclude from that then is dB, that will equal, rather dB, the magnitude of dB, rather dB is equal to the magnitude of the vector dB so I've got the magnitude of this result here, which is lambda minus 1 times the magnitude of A minus B. So knowing that, what we can do is find out what we know what lambda is. So with that, we can use our result for lambda to help us find out what dB is and what dA is. So let's focus on dA first. So let's just rub this out. That's equal to A over A plus B, and I'm timesing that by A minus B. So here we've got to work out, well, let's just double check this, we've got minus A plus lambda A minus lambda B plus B, which simplifies to lambda minus 1A plus lambda plus 1 minus lambda b. Now what I could do is actually redo this, so we will leave it alone. So here lambda minus 1, that's equal to a over a plus b minus 1 multiplied by a minus b, well, the magnitude of it. So I've got a minus, and then in brackets a plus b over a plus b, and I still want the magnitude of this actually, if we're being technical about things, then we should have the magnitude of this. And then here I've got a minus b. So what do I end up with? I've got the value of, well, the magnitude of minus b over a plus b times the magnitude of a minus b. So I end up with b over a plus b times the magnitude of a minus b. And so therefore what we can do now is find out the ratio of, if I go back to the question, we can find out the ratio of dA to dB. Now I know what dA is, we worked that out over here. So that was a over a plus b times the magnitude of a minus b. So therefore dA over dB, that's equal to a over a plus b times the magnitude of a minus b, and then I'm going to divide this result by b over a plus b times the magnitude of a minus b. And happily for us, that just leaves a over b. So I've got a over b for the ratio dA to dB. So therefore dA over dB is equal to OA over OB, which is equal to A over B. And so therefore we end up with the ratio dA to dB equaling OA to OB. Question number 6. Figure 1 shows a sketch of part of the curve with the equation y equals x times by the sine of the natural log of x, where x is greater or equal to 1. For x being greater than 1, the curve first crosses the x-axis at the point A. We have to find the x-coordinate of A. So, for part A, we have y equals x times by the sine of the natural log of x. And when y equals 0, you have x times by the sine of the natural log of x equaling 0. Now, x cannot equal 0 as x must be greater than 1. And so what we have then is the sine of the natural log of x equaling 0. And if we rearrange, well, if I take the inverse sine of 0, I get 0, then pi, then 2 pi, so on and so forth. So I've got the argument, which is the natural log of x, equaling 0, pi, 2 pi, so on and so forth, which means x is going to equal e to the 0, e to the 1, but rather e to the pi, e to the 2 pi, so on and so forth, which means the x coordinate of A is equal to e to the pi. So that's the x coordinate of A. For part B of the question, you have to differentiate x times the sine of the natural log of x and x times the cos of the natural log of x with respect to x, and then find the integral of sine of the natural log of x and the integral of cos of the natural log of x. Well, for this part, let's think about y equals x times the sine of the natural log of x. If I differentiate, I need to use the product rule. I've got x multiplied by the derivative of sine of the natural log of x, which is cos times the natural log of x, and then times by the differential of the bracket, that's 1 over x. And then I add on sine of the natural log of x times the derivative of x, which is just 1. And adding this up, we get cos of the natural log of x plus sine of the natural log of x. And if I've got y equals x times the cosine of the natural log of x, if I differentiate using the product rule, differentiating x, rather I've got x times by the differential of cos of the natural log of x, which is minus sine times the natural log of x times 1 over x, plus cos of the natural log of x times the derivative of x, which is just 1. And adding this up, I get cos of the natural log of x minus sine of the natural log of x. And what I need to do in this question is integrate sine of the natural log of x and cos of the natural log of x. So how could we do this? Well, if I call this equation 1, the derivative equation 2, this equation 3, and this equation 4, well, if I had 1 plus 3, then I would have y equals x times by the sine of the natural log of x plus x times by the cos of the natural log of x. And then if I differentiate this, well, let's call this 5. And if I differentiate 5, dy over dx, that will equal dy over dx, if I add together the derivative of x times the sine of the natural log of x, I have the cosine of natural log x plus sine of natural log x plus the cosine of the natural log of x minus the sine of natural log x. And so what I end up with is 2 times by the cosine of the natural log of x. And if I have equation 1 subtract equation 3, so now if I have equation 1 subtract equation 3, I would have my function being x times by the sine of the natural log of x minus x times by cos of the natural log of x. Now let's just call this 6. And if I differentiate 6 with respect to x, this is equal to the same thing as this, but this time I'm subtracting. So cos of the natural log of x subtract cos of the natural log of x, that's going to be 0, and then I've got sine of something minus sine minus the minus sign, so that's going to be positive 2 times the sine of the natural log of x. So what we need to do, going back to the question, is integrate sine of the natural log of x and cos of the natural log of x. So let's work out what would happen if I integrate the sine of the natural log of x. Well, the fundamental theorem of calculus tells us that if we have the derivative, we can integrate that to get the original function y. So the way to think about this is, well, I know that if I integrate 2 times the sine of the natural log of x, I end up with this result here. I end up with equation 6. So integrating sine of the natural log of x, that's going to be half this result. So that's going to equal 1/2 times by x times by the sine of the natural log of x minus x times by the cos of the natural log of x plus some constant, we'll call it k1. And if we factorize out the x with it, we've got 1/2 x multiplied by sine of natural log x minus cos of natural log x plus k1. And similarly, if I integrate cos of natural log x with respect to x, then what I will end up with, well, if I integrate 2 times the cos of the natural log of x, I end up with x sine natural log x plus x cos of the natural log x. But I've got half of that because I've only got a single cos. So I've got 1/2 multiplied by x times by the sine of the natural log of x plus x times by the cos of natural log x plus k1. And if I factorize out an x, I've got 1/2 x multiplied by the sine of the natural log of x plus the cosine of the natural log of x plus k2. And that's exactly what we wanted to show. Now for part C, for the first part, we have defined the integral of x times the sine of the natural log of x with respect to x. So what we need to do for part C, for the first part, is integrate x times by the sine of the natural log of x. Now, the first thing we can do is use integration by parts. And if we were to use integration by parts, u is equal to x, u dash is equal to 1, v dash, that's equal to the sine of the natural log of x. Now, integrating the sine of the natural log of x we've already worked out before. So we can find out what v is. V is equal to 1/2 x times by the sine of the natural log of x minus the cosine of the natural log of x. So now that we know what this is, what we can now do is integrate as regular. So what we have then is the integral of x times by the sine of the natural log of x equaling, well, I've got u times by v, so that's going to be 1/2 x squared times by the sine of the natural log of x minus the cosine of the natural log of x, and then we subtract the integral of vu dash. So we subtract the integral of vu dash, so I've got 1/2 x times by the sine of the natural log of x minus the cosine of the natural log of x dx. Now, what we'll do is we'll expand for the integral. So I've got 1/2 x squared times the sine of the natural log of x minus the cosine of the natural log of x, subtract 1/2 times the integral of x times the sine of the natural log of x, and then we've got plus 1/2 times the integral of x times by cos of the natural log of x dx. Now, do you notice how here we've got a 1/2 times the integral of sine of the natural log of x, which is what we have here. And so what we can do is add that to the left hand side. So I've got 1 plus 1/2, which is 3/2. So what I have then is 3/2 times the integral of x times the sine of the natural log of x dx equaling 1/2 x squared times by the sine of the natural log of x minus the cosine of the natural log of x, and then I add on 1/2 times the integral of x times by the cosine of the natural log of x dx. Now the issue is, so far I don't know what this is over here. I need to work that integral out. Well, first of all, before we do anything else, we can multiply through by 2. And so multiplying through by 2, we end up with this result here. Now, I'm going to have to integrate x times by the cosine of the natural log of x with respect to x. So let's do that at the side. So if I was to integrate x times by the cosine of the natural log of x with respect to x, well, same idea here. U is equal to x, u dash is equal to 1, v dash is equal to cos of the natural log of x, v is equal to the integral of this, which is, well, we worked it out previously, that was given by 1/2 x times by the cosine of the natural log of x. Actually, we'll write this as sine of the natural log of x plus the cosine of natural log x. So now we need to integrate this. So if we integrate x times by the cosine of natural log of x, we've got uv, so that will be 1/2 x squared times by the sine of the natural log of x plus the cosine of the natural log of x minus vu dash, so minus integral of vu dash, so that's minus 1/2 x times by the sine of the natural log of x plus the cosine of the natural log of x dx. So if we were to integrate this, well, what we can do is expand out to begin with. So I've got 1/2 x squared times by the sine of natural log of x plus the cosine of the natural log of x, and then we've got minus 1/2 of the integral of x times by the sine of natural log x, and then we've also got minus 1/2 times the integral of x times by the cosine of natural log x dx. Now, same idea. Here I've got minus 1/2 x cos of the natural log of x with respect to x. And if I add that over to the other side, we would have 3/2 times the integral of x times by the cosine of the natural log of x with respect to x equaling 1/2 x squared times by the sine of natural log x plus the cosine of natural log x minus 1/2 the integral of x times by the sine of natural log x dx. And now what we can do is multiply through by the 2. So here is our integral. We've got 3 times by the integral of x times the cosine of the natural log of x with respect to x equaling x squared times by the sine of the natural log of x plus the cosine of the natural log of x minus the integral of x times by the sine of the natural log of x. Now, if I call this I, and if I call this II, what I can do, well, here I want to get rid of this bit, because then I'll have something involving the integrals of sides only. So I'm going to multiply I by 3. So if I multiply equation I by 3, we'd end up with this equation here, 9 times the integral of x times the sine of the natural log of x equaling 3x squared times sine of the natural log of x minus cos of the natural log of x plus 3 times the integral of x times the cos of the natural log of x. And if I call this I, I can replace the 3 times x times the cosine of the natural log of x with what we worked out in the second equation. So I will substitute in the second equation into the third one. And if I do that, we've got 9 times the integral of x times by the sine of the natural log of x with respect to x equaling 3x squared times by the sine of natural log of x minus the cosine of the natural log of x plus 3 times, rather, I've already worked out the result. I've got x squared times by sine of natural log x plus cos of natural log x, subtract the integral of x times by the sine of natural log x dx. And if I add the x sine natural log of x to both sides, then we have 10 times the integral of x sine of natural log of x equaling 3x squared times by the sine of natural x minus the cosine of natural log x plus, here I'm going to expand this as x squared times by the sine of natural log x plus, well, let's expand here as well. I've got this, and then I've got minus 3x squared times this, and then I've got a x squared times by the cosine of the natural log of x. So, working out what this is, I've got 3x squared plus another x squared, so that's going to be 4x squared times the sine of natural log x, and then I've got minus 3x squared plus another x squared of the cosines, so that's minus 2x squared times by the cosine of natural log of x. And if I factorize out a 2x squared, I have 2x squared times by 2 times by the sine of natural log x minus the cosine of natural log x. And what I need to do now is find out what the integral of x times by the sine of the natural log of x is. So the integral of x times by the sine of natural log x with respect to x, that's equal to, now here I'm going to have 1/10, because I've got, rather here I'm going to have 1/5, because I've got 2 divided by 10, multiplied by x squared multiplied by 2 times by the sine of natural log x minus the cosine of natural log x, as we see here. So that is the result. And then I've got a constant of integration, we'll call it k. Now we have to show that the area of the shaded region are bounded by the curve, and the x-axis between the points 1 and 1, 0 and a is 1/5 e to the 2 pi plus 1. And we already know what the coordinates of a are. That's e to the pi 0. So for the next part of part C, the area will equal the integral from 0 to e to the pi of x times by the sine of natural log of x dx. So if I work out what this is, well, what I'm going to be doing is evaluating 1/5 x squared times by 2 times by the sine of natural log x minus the cosine of natural log x. I'm going to evaluate this in between 0 and e to the pi. So that's how we work out the area. And therefore, for my upper limit, I have we can get rid of these. Well, we need the brackets here. For the upper limit, we have 1/5 times by e to the pi squared multiplied by 2 times the natural log of, or rather 2 times by the sine of the natural log of e to the pi minus the cosine of the natural log of e to the pi. So this is what we have for my upper limit. And for the lower limit, we have 1/5 times by 0 squared multiplied by 2 times by, rather here, my lower limit's 1. So I've got 2 times by the sine of the natural log of 1 minus the cosine of the natural log of 1 and then let's evaluate this. So I've got here 1/5 e to the 2 pi, because I've got e to the pi squared, and then inside this bracket I've got 2 times by the sine of, now here I've got the natural log of e to the pi, which is just pi. So I've got here the sine of pi minus the cosine of pi, same idea. The natural log of e to the pi is just pi. Then I subtract, well here I'm just going to end up with 0. So I don't need to worry. Rather, here I've got 1/5 times by 1, so that's just 1/5. And then I've got here 2 times by the sine of 0 minus the cosine of 0. So I've got 1/5 e to the 2 pi Now here, the sine of pi is 0, so I've got 0 minus, and the cosine of pi is minus 1, so here I've got 0 minus 1 minus 1/5. I've got here 0 minus 1. And so therefore, what we end up with is 1 in this bracket. So I've got 1/5 e to the 2 pi times by 1 minus 1/5 of minus 1. And therefore, factorizing out a 1/5, we can therefore conclude that R has an area of 1/5 e to the 2 pi plus 1 unit squared. Question number 7. Figure 2 shows a rectangular section of marshland or ABC, which is A meters long by B meters wide, where A is greater than B. Edgar intends to get from O to B in the shortest possible time. In order to do this, he runs along the edge OA for a distance x meters, where x is in between 0 and A, to the point D before wading through the marsh directly from D to B. Edgar can wade through the marsh at a constant speed of 1 meters per second, and he can run along the edge of the marsh at a constant speed of lambda meters per second, where lambda is greater than 1. And for part A, by finding an expression in terms of x for the time taken t seconds for Edgar to reach B from O, we have to show that dt over dx is equal to 1 over lambda subtract a minus x over the square root of a minus x squared plus b squared. Now, first of all, we can see that the distance d to a is a subtract x. I've got a subtract x gives me the distance dA. And now we can use Pythagoras to find out what dB is. So, using Pythagoras, dB is equal to a minus x squared plus b squared. And now we can find the time. So for the time, from O to D, we've got a distance x and we've got a speed lambda. So the time from O to D is x over lambda, and then we will add on to this the time taken from D to B. Now we know what dB is. That's equal to a minus x squared plus b squared, then square rooted. And then I'm going to divide this by the time it takes. Well, that time, we are told in the question, is, rather that speed is 1 meters per second. So we divide by 1. And so therefore, we can see t is equal to x over lambda plus the square root of a minus x all squared plus b squared, which I'm going to rewrite as a subtract x squared plus b squared to the power of 1/2. And now we need to differentiate. So if we differentiate to find out what dt over dx is, while differentiating x over lambda, we end up with 1 over lambda. And differentiating, well, here we need to use the chain rule. So I times by the power, and then I subtract 1 from the power, so I've got a minus x squared plus b squared to the negative 1/2. And then we multiply by the differential of the bracket. Now the differential of the bracket, I need to differentiate a subtract x squared. And using the chain rule again, we've got the 2 multiplied by a minus x multiplied by the derivative of this bracket, which is minus 1. And so, if we tidy this up, we can see that dt over dx, that's equal to, well, I've got the 1 over lambda, and then I've got the half and the 2 simplifying to 1. I'm multiplying that by negative 1, so I've got minus, and then I've got a minus x, and then I'm multiplying this by a minus x squared plus b squared to the negative 1/2, which is the same as a minus x squared plus b squared and square rooted. And that's exactly what we wanted to show. For part B, for the first part, we've defined in terms of a, b and lambda the value of x for which dt over dx is equal to 0. Well, for the first part of part B, if we have dt over dx equaling 0, we've got 1 over lambda subtract a minus x over the square root of a minus x squared plus b squared equaling 0. And what we need to do is find out the value of x. Well, if we rearrange, we have a subtract x over the square root of a minus x squared plus b squared equaling 1 over lambda. And so if we cross multiply, we have lambda multiplied by a minus x equals 1 times by the square root of a minus x squared plus b squared. And now if we square both sides, we have lambda squared multiplied by a minus x squared equals a minus x squared plus b squared. And if we take everything over to one side involving an a minus x all squared, we have lambda squared multiplied by a minus x squared subtract a minus x squared equals b squared. And therefore, we've got a minus x squared multiplied by lambda squared minus 1 equals 0. Rather equals b squared. And so, a minus x squared is equal to b squared over lambda squared minus 1. And now if we square root, we have a minus x equals plus minus b squared over lambda squared minus 1, then square rooted. And because we have x being less than a, we need to take the positive square root. So we have a minus x equals the positive square root of b squared over lambda squared minus 1. Then we have this being square rooted. And that's because x is less than a. And just as a side note, the reason we want x being less than a, well, if I rearrange for x, we have x equaling a subtract. Well, here, if I've got b squared over lambda squared minus 1 square rooted, that's the same as b over lambda squared minus 1 then square rooted. And the reason, just as a side note, if we have x being less than or equal to a, we have a subtract b over lambda squared minus 1 square rooted being less than or equal to a, which is why we need to take the positive square root, because here we will have no solutions then. So this condition satisfies x being less than a. And that's the result we wanted to show. Now, for this particular value of x, we have to show that this value of x lies in the interval 0, which is less than or equal to x, which is less than a, provided lambda is greater or equal to the square root of 1 plus b squared over a squared. Well, if we consider the situation where x is greater or equal to 0, then we have a subtract b over lambda squared minus 1 square rooted being greater or equal to 0. So, if we rearrange, we have a being greater or equal to b over lambda squared minus 1 square rooted, and so lambda squared minus 1 square rooted is greater or equal to b over a. Squaring both sides, lambda squared minus 1 is greater or equal to b squared over a squared, and adding 1 to both sides, we have lambda squared being greater or equal to 1 plus b squared over a squared, which means lambda is greater or equal to 1 plus b squared over a squared, then square rooted. Now we have to show for the third part, for theta in this range, we have to show that the value of x found in the first part of part b gives the minimum value of t. So we need to show that the value we found is a minimum, which means we have to differentiate once again. So here I've got dt over dx, but what I've done this time is instead of having the square root, I've raised it to the power of 1/2. So now to differentiate this once again, we need to use the quotient rule. So if we were to use the quotient rule, u is equal minus, and then in brackets, a minus x, so therefore u dash is equal to 1, and we've got v, which is equal to a subtract x squared plus b squared to the 1/2, and therefore v dash is equal to 1/2 multiplied by a minus x squared plus b squared to the negative 1/2 multiplied by 2 multiplied by a minus x to the 1 multiplied by minus 1. And so if we simplify all this, what we will end up with is v dash equaling minus, then in brackets, a minus x, and then I'm going to divide this by a minus x squared plus b squared to the 1/2. So now we can find out what d squared t over dx squared is using the quotient rule. So d squared t over dx squared, what we have is v, which is a minus x squared plus b squared to the 1/2 times by u dash, subtract, and then here I'm going to write this in an entire bracket, we've got here v u dash subtract u, which is minus a minus x, times by v dash, which is minus a minus x over a minus x squared plus b squared to the 1/2. And then what we need to do is divide this entire result by v squared. So I'm going to divide this by v squared, so that is a minus x squared plus b squared to the 1/2, and then this is being squared. So now let's try to simplify this even further. We've got here a minus x squared plus b squared to the 1/2, and then we've got this minus, and here we've got a minus x times a minus x, and then we've got the two minuses giving a plus, so I've got the minus and the plus which give a minus, so I've got a minus x squared, and then I'm going to divide this by a minus x squared plus b squared to the 1/2, and then we're going to divide this entire thing by a minus x squared plus b squared to the power of 1. And now if I multiply through by a minus x squared plus b squared to the 1/2, we have a minus x squared plus b squared to the 1/2 times by a minus x squared plus b squared to the 1/2, subtract a minus x squared, and then I'm going to divide this result by a minus x squared plus b squared multiplied by a minus x squared plus b squared to the 1/2. So here, something to the half times something to the half, that just gives the something. So we've got a minus x squared plus b squared, and then we subtract a minus x squared, and then I'm going to divide this by a minus x squared plus b squared to the 3/2. And that's exactly what we need, because what we can now see is what we'd end up with on the top is just b squared, because the a minus x all squared simplifies, and then on the bottom we've got a minus x squared plus b squared to the 3/2. And this value here is greater than 0 for all values of x. Well, for all real values of x. And the reason for that is whatever real value of x I have, because I'm squaring it, I'm going to get a positive number, and because b is greater than 1 and a is greater than 1, b squared is going to be greater than 1, so this result will always be greater than 1. And therefore what we have then is a minimum. Now we have to find the minimum time taken for Edgar to get from O to B if lambda is greater than the square root of 1 plus b squared over a squared. And if we remember from the second part of B and the first part of part B, we found a particular value of x for which we have lambda being greater or equal to the square root of 1 plus b squared over a squared. And so therefore, what we have is that particular value, x equaling a minus b over the square root of lambda squared minus 1. And what we can do is substitute this into our value for t. So here is our value of x, and here is how we find out what t is. So what we need to do is replace x with a minus b over the square root of lambda squared minus 1. So if we work this out, we have t equals, well, here we've got a minus b over lambda squared minus 1 square rooted plus, well, here then I'm going to divide this by lambda, and then here I'm going to have a subtract, and then in brackets a subtract b over lambda squared minus 1, and then this is squared, and then I add on b squared, and then I square root. So now we need to simplify all this. So let's think about what we end up with. Well, here I can rewrite this as a over lambda subtract b over lambda multiplied by lambda squared minus 1 plus, now inside here we have a minus a, and then we've got the minus and the minus giving a plus. So I've got here b over lambda squared minus 1 square rooted and squared plus b squared, and then this is square rooted. So now let's try to simplify this even further. We've got t equals, well, this bit's going to remain the same. And then here, we're going to have b squared over lambda squared minus 1 plus b squared. Then this is square rooted. So now we can simplify this. Well, what we can do, if we simplify this, we can rewrite this as b squared plus b squared times lambda squared minus 1 over lambda squared minus 1. And so what we'd end up with here is, well, if I copy and paste this, b squared plus b squared lambda minus b squared, this bit over here is going to simplify to just b squared lambda squared. So we have t equals a over lambda minus, now here this bit remains the same, and then here we would have on the top b lambda. Now to simplify this even further, we've got a over lambda subtract b over lambda times by lambda squared minus 1. And then here what I can do is have a lambda times by lambda squared minus 1 square rooted, and then here on the top I need b lambda squared, or in other words lambda squared b. And if I factorize out a 1 over lambda, then I would have a minus then on top here we've got b plus lambda squared b over lambda squared minus 1 square rooted, and we can simplify this even more. We've got t equals 1 over lambda multiplied by a plus b multiplied by lambda squared minus 1 over well, here we'd have lambda squared minus 1 square rooted, and therefore recognizing that lambda squared minus 1 over the square root of lambda squared minus 1 is just lambda squared minus 1 square rooted, what we can conclude then is t equals a plus b times by square root of lambda squared minus 1, and then I'm going to divide this by lambda. Now we have to find the minimum time taken to get from O to B if lambda is in between 1 and the square root of lambda, the square root of 1 plus b squared over a squared. So the way to think about this, so to minimize t, as lambda decreases, x decreases, and we have shown that when lambda is equal to the square root of 1 plus b squared over a squared, x is equal to 0. And so, since x is a distance, it can't be negative, so once it gets to 0, it sticks to that value even when lambda decreases more. And so for smaller values of x, rather for smaller values of lambda, x is equal to 0. So here is our formula for t in terms of x. And what we're going to do is replace the x with 0, and that leaves us then with t equaling a squared plus b squared square rooted. Now, Edgar's friend Frankie also runs at a constant speed of lambda meters per second. Frankie runs along the edges OA and AB, and given that lambda is greater than the square root of 1 plus b squared over a squared, we have to find the range of values for lambda for which Frankie gets from b to O in a shorter time than Edgar's minimum time. So Frankie goes from OA and then AB, so OA and then AB. So what's that distance going to equal? That distance is going to equal A plus B, and the speed is lambda, and therefore for part D of the question, the time for Frankie, that's equal to A plus B over lambda. And we know that the time for Edgar, that's equal to, well, we've just found this out to be this over here. The time for Edgar is A plus B multiplied by the square root of lambda squared minus 1 over lambda. And what we know in this question is the time for Frankie is less than the time for Edgar. So we have A plus B over lambda being less than A plus B times the square root of lambda squared minus 1 over lambda. So now let's find out the range of values for lambda. Well, if we cancel the lambdas from the top and bottom, we have A plus B being less than lambda plus B times lambda squared minus 1 square rooted. A is cancelled, so we are left with B being less than B times lambda squared minus 1 square rooted. So we've got 1 being less than lambda squared minus 1 square rooted. Square both sides, so we've got 1 being less than lambda squared minus 1. 2 is less than lambda squared, and therefore lambda is greater than the square root of 2 only. We need the positive solution only.